Have you ever just stopped and thought about the quiet little bits of magic that happen in your kitchen every day? Well, today we're going to solve a big one. How on earth do oil and water, two things that famously hate each other, get together to create those creamy, amazing textures we love? Yeah, let's get into it.
I mean, it's a classic kitchen mystery, right? You shake up a vinaigrette with all your might, and literally 2 minutes later, you can see it separating back into layers. And yet, mayonnaise, which is mostly oil and just a bit of water, stays perfectly creamy and mixed for weeks on end. The secret isn't some kitchen voodoo, it's actually some really clever chemistry.
And this picture, well, it pretty much says it all. This is the natural state of things, oil floating on top of water. In science speak, we call them immiscible, a fancy word that just means they refuse to mix. But why? What is actually physically keeping them apart? To figure that out, we've got to zoom way in to the molecular level.
Okay, so here's our game plan. First, we're going to look at the standoff between oil and water. Then, we'll dive into the science of how things mix in general, and that'll lead us to the world of emulsions. We'll meet our hero, the molecular matchmaker, crack its secret code, and finally, see how this all shows up right on your plate.
So how do we get these two to cooperate? Well, before we can get them to play nice, we have to understand the forces that are keeping them in separate corners. And it all starts with a concept you probably haven't thought about since high school science class. And that concept is surface tension. The best way to picture it is like an invisible skin on a liquid. See, water molecules are super attracted to each other. They'd much rather hang out with other water molecules than with, say, the air, or in our case, oil. This creates this incredibly strong inward pull, making the surface tight and cohesive, almost like a tiny invisible force field. And here's what's happening on that microscopic level. The molecules deep inside the liquid, they're getting pulled on equally from all sides by their neighbors. But the molecules right at the top, at the surface, they're different. They only have other molecules pulling them from below and from the sides, so they get pulled inwards, and that's what creates that strong elastic-like tension. Now, when you try to force two different liquids together, that surface tension gets a new name: interfacial tension. It's the force happening right at the boundary, the interface, between them. It's that powerful urge for water to stick with water and oil to stick with oil. That's the barrier we have to overcome.
So with this incredibly strong force working against us, how does anything ever get mixed? Well, it turns out that pretty much every food we eat is a type of complex mixture called a dispersion. Let's figure out where our oil and water problem fits into this bigger picture.
Okay, so what is a dispersion? It's actually really simple. You have a dispersed phase, that's the stuff being scattered around, and a continuous phase, that's the medium it's being scattered in. So in our vinaigrette, the little oil droplets are the dispersed phase, and the vinegar they're floating around in is the continuous phase. Easy enough.
But here's the thing, not all dispersions are created equal. It really all comes down to the size of the particles. On one end of the spectrum, you've got true solutions. Think salt dissolved in water. The particles are tiny and it's super stable. On the total opposite end, you have suspensions, like sand in water. The particles are huge and they settle out almost immediately. The real magic for us happens right in the middle, in what's called a colloidal dispersion. And that brings us to the specific type of colloidal dispersion that holds the key to our entire kitchen mystery. It's time to talk about emulsions.
So here's the big reveal. An emulsion is what we call it when we successfully scatter one liquid, like oil, into another liquid it shouldn't mix with, like water. Mayonnaise, milk, butter, salad dressing, even hand lotion. They are all emulsions. They are essentially a scientific victory over that interfacial tension we were just talking about. Now, emulsions come in two main flavors. You've got oil and water, or OW, where you have tiny little droplets of oil scattered through water. That's your milk and your mayonnaise. And then you have the complete opposite, water and oil, or WO, where tiny droplets of water get trapped inside a sea of oil, and that's your butter and margarine.
Okay, but how? How do we get these tiny droplets to actually stay scattered? Just shaking them up isn't enough, we've seen that. They'll just separate again. We need a secret agent, a molecular peacemaker. We need an emulsifier.
So what exactly is an emulsifier? Well, the official definition says it's a substance that consists of both a polar group and a nonpolar group. In simple terms, it's a molecule with a split personality. It has one part that's attracted to one liquid and another part that's attracted to the other.
And this amazing dual nature has a fantastic name, amphiphilic. The molecule has a hydrophilic head, that's the water-loving part, and it has a hydrophobic tail, which means water-fearing. And it just so happens that this water-fearing tail absolutely loves oil.
So this molecule can basically act as a perfect translator between the two.
And check out how it works. When you add an emulsifier to the mix, these little molecules rush to the battlefront, that interface between the oil and water. Their water-loving heads stick out into the water, and their oil-loving tails bury themselves in the oil droplets. They literally form a protective shield around each tiny droplet, physically stopping them from glomming back together. It's brilliant.
But you can't just throw any emulsifier into any situation. There's specialized tools. Food scientists needed a way to pick the right one for the job, so they came up with a system, a kind of cheat sheet, called the HLB scale.
The hydrophilic lipophilic balance, or HLB. Yeah, it's a mouthful. Let's just call it HLB. Think of it as a rating system. It's just a number on a scale that tells you how much an emulsifier prefers water versus how much it prefers oil. A low number means it's an oil lover. A high number means it's a water lover.
And this number tells you exactly what job that emulsifier is good for. If you want to make a water in oil emulsion, like butter, you need an oil-loving emulsifier with a low HLB value, somewhere between 3 and 6. But if you want to make an oil in water emulsion, you need a water lover with a much higher HLB, something between 8 and 18.
So let's bring it all back home to our mayonnaise mystery. Mayonnaise is an oil in water emulsion, so we need a water-loving emulsifier. Well, guess what? The lecithin that's naturally in egg yolks has an HLB value smack dab in that 8 to 18 sweet spot. That's it. That's the secret to its perfect, creamy stability.
And this isn't just something that happens in a lab. This is happening on every single shelf of your grocery store. Emulsifiers are the unsung heroes behind the texture and stability of so many foods you eat every day. So here's a little challenge for you. Next time you're reading an ingredient label on ice cream, bread, salad dressing, whatever, keep an eye out for these names. You'll see lecithin all the time, usually from soy. Mono and diglycerides are in pretty much everything. And things like polysorbates keep whipped toppings from falling apart. You can actually spot the science in action. So there you have it. The case of the creamy mayonnaise is officially closed. We've seen that your kitchen is basically a laboratory full of fascinating, invisible chemistry. So the next time you whisk up a sauce or scoop some ice cream, what other hidden science are you going to discover?